can use it to do hydrogen economy, and then these renewable sources are not constant over time, and they are pretty much localized. So you would need some energy storage, for example, like batteries. Then meanwhile, in the near future, the economy is going to be heavily dependent on carbon-based energy as well. So that there's a lot of CO2 that we can handle, we need to handle, and if we can make use of some renewable energy to convert, for example, carbon dioxide back to fuels and then use for chemical products, that would be a nice thing to do. Right? Then if we look at this reaction, right, so electrochemical carbon dioxide conversion, typically you have an electrolyzer, then on one side where you have cathode where reduction reactions take place, right, and carbon dioxide is getting reduced. And then typically on the other side, you get some oxidation reaction going on. For example, water is getting oxidized to oxygen. Right? Then if we look at the carbon dioxide reduction reactions, something that you can immediately realize is there are so many possible products. Right? I mean, if you reduce CO2 from oxidation state of carbon 4, you go to formic acid, formaldehyde, methanol, methane, carbon monoxide, all this kind of stuff. Then if we talk about two CO2 molecules or their intermediate, their reduction intermediates can combine to form carbon-carbon bonds, then there's basically a huge number of possible products, right? So one thing that electrochemical carbon dioxide reduction reactions are not so good at is the selectivity, right? So how you actually control, where the electrons go to specific products. Right. Then the table here lists the standard reduction potentials of these reactions going from carbon dioxide to different reduction products. And if you look at those numbers are not too far away actually from the standard hydrogen electrode. So essentially the theoretical potential that you need to reduce carbon dioxide is more or less the same as what you would need to reduce, for example, protons to hydrogen. But in reality, in the devices, you would actually need to spend a lot more to do that. Sometimes the overpotential is 500 millivolts. Sometimes it's as high as 1 volt that you would have to spend basically to accelerate the reactions. Right. So the challenges with this reaction is how you control the selectivity to go to the desired products, and how you actually increase the activity to make that reaction to be more energetically efficient. Right. And we certainly need a catalyst, right? Then speaking of catalysts, there are generally two types of catalysts. One's homogeneous, meaning that the catalyst itself is dispersed in the same phase as your reactants and the products. And this is an homogeneous catalyst that often small molecules. For example, they are widely used in the pharmaceutical industry for organic synthesis, like molecules dissolved in solution. Right? And these homogeneous catalysts are really efficient, and from the single site perspective. And also, I mean, as long as the molecular structure stays stable, then you can basically connect the catalytic properties back to the structure, so you know what your catalytic site is, and there can be a relationship established between the structure and then the catalytic properties, and then you can actually study the reaction mechanism. Right? Then another side of these catalysts is these heterogeneous catalysts, right? So these ones are like that, right? So they basically operate in different phases of reactants and products, and this is widely used, for example, in the chemical industry, where you use a solid catalyst to run gas phase or liquid phase reactions. So the advantages are also pretty clear, right? I mean, you have a catalyst that can be easily separated and then recycled, and then they are very effective. And then one more thing is they are compatible with electrochemical devices. So if we think about the electrolyzers, fuel cells, pretty much they all use heterogeneous catalyst, right? But the problems with the heterogeneous catalyst is, it looks like that, right? It's usually made of a lot of nanoparticles with different sizes and shapes. And for those nanoparticles, they sometimes have ligands on the surface, they have supports, or they have promoters. So basically, it's fair to say that for a specific catalyst, the surface where the catalytic reaction takes place has a lot of different catalytic sites, right? And it's very hard to correlate the catalytic property to a specific type of structure, and then to understand more about this structure reactivity correlation, right? So So we were thinking that if we can actually combine, the advantages of these two types of catalytic system and see if you can get it to some catalyst that can have their both advantages. For example, we can build molecular structure-based catalyst, but they are still heterogeneous, or whether we can use the molecular concepts to guide the design of nanoparticle-based catalyst and try to, make use of the multi-component cooperation to get to more interesting catalysis. Right? So what we started off was, we take some molecular structures that had been known to be active for electrochemical CO2 reduction. Then we make heterogeneous catalyst out of them and see what they can do. Right. So we started from these, metal porphyrin based structures that has these phenolic groups attached to the molecular structure. So those ones were known to be, active for CO2 reduction in homogeneous case, say in organic solutions, right? And what we did was we simply just put them onto electrodes, right? Then instead of using organic electrolyte, which those molecules would dissolve, we simply just use aqueous solution, so that now those molecules would not dissolve in the electrolyte, they would just stay on the surface of the electrode, then it automatically becomes a heterogeneous electrode. I mean, certainly, as I would say later, that this is not a good way of getting the most efficient catalyst, but it works, right? So it gives you at least a heterogeneous catalyst that you can look at its catalytic properties, right? So that's what we did to begin with, and all those metal porphyrin complexes were provided by my colleague Professor Gary Goodwick's group. Okay, so we did that, right? And the first thing that we actually looked at is the structure of this complex, right? So we varied the identity of the metal ion first. And then if we go to, for example, magnesium or zinc as the metal ion, then pretty much they're not very active for CO2 reduction. Instead, in this aqueous solution, they catalyze water reduction, and H2 is the major product, so it runs all the side reactions, right? Then if we go to Then if we go to iron or cobalt or nickel as metal centers, then they are pretty much CO dominant, right? So that is the major product, and this is pretty much consistent with others that are seen, for example, in homogeneous catalysis in organic solvent. Okay. Then we went to a different metal ion, which is copper. Then it's quite interesting that with copper as the metal ion, now we start to see something different, and then we actually saw some hydrocarbons, methane and then ethylene, up to 40% of ferritic efficiency. And then if you look at the catalytic behavior, it behaves like a molecular catalyst. As you sweep the potential to more negative direction, you actually see a redox wave, right? And before and after that redox wave, the catalytic selectivities are different. So before it gets reduced, CO2 mostly gets reduced to carbon monoxide. But after the redox wave, you start to see that the methane becomes the dominant product. Even though that in the entire range, we have quite a lot of side reactions from water reduction. But we get a hydrocarbon as a product. And then this thing is actually dependent on the ligand as well, right? So if we switch from these ligand that had the phenolic groups to those methoxy-based phenol groups, then we find that the selectivity for methane is lower, but it has more CO in the products. Then if we further change the ligand to the thiocyanine-based, from the porphyrin to the thiocyanine, then we could actually increase the selectivity to methane, and this one actually gave like 6% selectivity for methane, right? So at that time, one question that came up to us is, what was the catalytic sites that are doing this carbon dioxide conversion, right? And then we looked at the catalyst before the reaction, and then we looked at the catalyst after the reaction, and we found that the molecular structures were still intact after the catalysis. It's verified by, for example, UV-Vis, fluorescence, mass spec. We still find the same complex structure. So that once led us to the conclusion that the molecular structures are the active sites that were doing this reaction. Then it wasn't really clear because, if you're familiar with carbon dioxide reduction on metal complexes, almost all the metal complexes reduce the CO2 either to formic acid or to carbon monoxide. It's very rare for molecular catalyst to reduce carbon dioxide to, deeper product, like a deeply reduced product like methane. And it's even more surprising that you can actually have carbon-carbon coupling to make some of this ethylene, right? So we had that question, and with that question in mind, we actually looked at the catalytic structure actually under the electrochemical conditions and see whether there's anything different from what we have seen before and after the reaction. So we did actually absorption spectroscopy under electrochemical conditions, in collaboration with my Professor Deng Xinfeng's group at Oregon State University. So we looked at the copper thiocyanine structure, right, under electrochemical conditions. And the left one is the near edge X-ray absorption. So basically it tells you the electronic structure, the oxidation state, etc. Right? And to begin with, you get a copper 2+. Then if we go to the negative potential where CO2 is actually reduced to methane, we actually see that the copper 2+ actually gets reduced to copper 0, right? And then after you release that the negative potential, the oxidation state goes back to copper 2+. Okay. Then on the right-hand side, we have the extended range of that X-ray absorption spectra, which actually tells you the coordination number, atomic distance, etc. Right? So now if we look at the coordination, to begin with, it has this copper-nitrogen coordination, as in that copper thiocyanine molecular structure. Then you go to the working condition where methane is produced. Actually, the carbon-nitrogen coordination is gone, and you actually see the copper-copper coordination. Then after you release that reductive potential, then it goes back to this copper-nitrogen coordination, right? So now if we look at the actual species, the real species that are doing the catalysis, it seems like it's something that has an oxidation state of 0 and it has copper-copper coordination. So it is actually a metallic copper type of structure. Then we can actually do more analysis on this extended range of X-ray absorption, and we can analyze the coordination number. And based on the coordination number, we can deduce the size of that metallic copper species, right? And the result is, if you go to negative potential, right, you get a coordination number of 4 and between 4 and 7, and which is actually corresponding to a size of 1.5 to 2 nanometers under that working potential condition. So we're actually forming very small metallic copper clusters that is catalyzing carbon dioxide to methane. And after you actually release that negative potential, then those metallic copper clusters, they go back to that molecular structure. So it is a restructuring, but it is reversible restructuring that is dependent on the electrode potential. Right? So the understanding is you have this copper thiocyanine structure to begin with, then you go to negative potential, it gets reduced to small copper clusters. And the copper cluster is actually capped by those empty thiocyanine ligands, which limit the size to be very small, and that's related to the high selectivity to methane. And after you release that potential, the copper can be reactized back to the, and go back to the copper thiocyanine molecular structure. And this is unique to that thiocyanine ligand or that porphyrin ligand. If we switch to, for example, carboxylic acid-based ligand or other nitrogen-based ligand, they do not work that way. The copper gets reduced, but it forms very large metallic copper nanostructures, and it's not reversible. Okay? So in this case, we see a reversible restructuring of metal complex to do carbon dioxide reduction. And then even in this case, where you actually have a restructuring, right, it is the metal center that gets reduced and then do the chemistry. And this is the case for, in fact, for many other, of almost all the metal complexes where the metals ion gets reduced first, then to do the CO2 reduction chemistry. Right? Then we actually found something that is different from this zinc porphyrin structure. In this case, right, I mean, this is a zinc porphyrin molecule, and we found that in mixed water and then organic electrolyte, it catalyzes CO2 reduction to CO with pretty good selectivity up to 90%. Right? It's not really active, right, but it's quite a selective. Then the interesting thing about this one is if we do the same X-ray absorption spectroscopy on the reaction conditions, what you see is the oxidation state and the coordination number of the metal ion basically does not change. Right? So in that case, the oxidation state of zinc remains 2+, right? And the coordination remains zinc nitrogen. So there's nothing actually taking place to the zinc center. Rather, if you look at the potential dependent cyclic voltammetry, it shows that it gets a characteristic reduction peaks. So if we write it in argon, right, it gets a reduction peak, then 3 oxidation peaks. So that is a very characteristic behavior of the porphyrin ligand gets reduced and oxidized. Then if we do the same thing in carbon dioxide, which is the radial curve, then you see that it gets reduced, but now the oxidation curves are different because when you have CO2, then the reduced ligand will basically transfer the electron to the carbon dioxide. Then that does the reaction. So in this case, what we believe is now the metal center does not get reduced and transfer the electron. Rather, it works as a binding site for the CO2, but the electron actually comes from the ligand, which actually gets reduced first, then transfer the electron to the CO2 to do the chemistry. So this is a different way how the metal ion and the ligand work together to do the chemistry. And to verify this, we actually did some chemical reduction experiments. Right? So we actually reduced the zinc porphyrin chemically to show that it is indeed the ligand that gets reduced, right? Then we put in oxygen or carbon dioxide to show that that reduced the ligand, that reduced the molecule with the electron parked on the ligand that can actually react with O2 or CO2, then to give that electron back to those small molecules. Okay. So this is another case where the metal and the metal ion and the ligand work together to do CO2 reduction. And I was actually mentioning that in those cases where we actually just load a lot of molecules onto the electrode surface to form a film, right? To do, as a catalytic electrode, it is not a great way of getting an efficient electrocatalyst, simply because those organic compounds are not really conducting, right? And then once you pile a lot of them onto the electrode surface, the catalytic sites are not well exposed, right? So these are not good factors for an efficient electrocatalyst. So in order to do a good electrocatalyst, you want those active sites to be well dispersed. You want them to be sitting on something that is really conductive, right? So what we did is we made some assembly of these molecules with carbon nanotubes. So in this case, we use pi-pi interaction to put this cobalt tyrosine molecules onto the carbon nanotubes so that they get almost a monolayer-like dispersion on the surface. Right now, those active sites are dispersed, and those carbon nanotubes are really electron highways, right? So they can deliver the electron very efficiently to do the catalysis. And in this case, just by having those molecules on the carbon nanotubes, we can increase the reaction rate of CO2 conversion to CO by 50 times, right? And you get it to high current density. It's stable for 10 hours, right? And with a huge turnover number. Then the nice thing with this type of catalyst is it is heterogeneous, right? It is fast, but its catalytic site is still molecular. So we know what we actually have, and we actually have some understanding of the reaction mechanism, even though that we don't know every single step of it, but we actually know a little bit about this mechanism, which can be made use of to further improve the catalysis if we wanted to, right? And if we think about the catalytic mechanism, pretty much it is the cobalt 2 plus in the center that gets reduced to cobalt 1 plus first, right? Then the cobalt 1 plus is going to transfer the reaction to carbon dioxide, transfer the electron to carbon dioxide to make the COOH intermediate. Then it will be another proton addition and the electron addition to get it to the CO, right? So this is it has been made pretty clear by a lot of studies of homogeneous catalysis in the solution phase. So the active site is actually a cobalt 1 plus site, right? So if you can make that reduction from cobalt 2 plus to cobalt 1 plus take place at lower overpotential, your catalyst is going to be more active, right? So that's what we did, right? We actually anchored those 8 thionyl groups onto the ligand. And these are really strong electron withdrawing groups, right? So we make this cobalt center to be more positively charged. And the cyclic voltammetry shows now that the cobalt 2 plus can be reduced to cobalt 1 plus at more positive potential, or lower overpotential. And with that, we can increase the activity, right? Especially at this low overpotential range, you get a higher current density and a higher selectivity because the cobalt 1 is easier. So now we actually have a catalyst that is, highly active, good, larger current density, high selectivity, but it is also actually molecular in nature. The catalytic site is molecular in nature, and you can get it to high turnover frequency, and you can use some mechanism-based optimization to, improve its performance, right? So these are the stories that we actually have, we have had for molecular-based catalysts. Then we were actually thinking whether we can somehow make use of these molecular level concepts to design nanoparticle-based catalysts. So we were thinking if we can use nanoparticle as a ligand, right? And then we were thinking of actually 2 ways a nanoparticle can play. So one is a nanoparticle actually play as an electronic ligand. So I have particle A sitting together with particle B, then the particle A can either donate the electron to particle B or take electrons away from particle B, modifying the electronic density of the particle B and how it interacts with the intermediates. So I call that an electronic ligand. Then I was thinking of another way that the particle A can play, when the catalytic process is taking place on particle B, the particle A can provide a different type of sites that can work together with the sites on particle B to do catalysis. So I call that a cooperative ligand or dual site mechanism, something like that, right? So two ways of these things, right? Then to illustrate that, I just give an example that we have had in our lab. So this is the silver and tin oxide hybrid system. Right? The structure is I have very small, which is like 3 or 5 nanometers tin oxide nanoparticles sitting on the surface of larger silver nanoparticles, like 40 nanometers, right? And this catalyst is interesting in the sense that it shows potential dependent behavior, okay? So when the potential is not so negative, for example, at minus 0.6, the silver is the major catalytic site. The tin oxide serves as a promoter, and it helps the silver to convert carbon dioxide to carbon monoxide. Then if we go to a different potential, which is more negative, then the tin oxide becomes a major player, and the silver becomes a promoter. It helps the tin oxide to convert carbon dioxide to formic acid, right? So the data, right? If we look at the silver itself, it kind of reduces CO2 to CO, negative potential, not so selective, 70%, right? And then tin oxide, negative potential to formic acid, not so selective, 65%. Then if I put them together, right? First thing to note is, look at the red one, right? The tin oxide is really helping the silver to reduce CO2 to CO better. It gets shifted to lower overpotential, selectivity goes higher, right? Then the silver is also helping the tin oxide to better reduce CO2 to formic acid, gets higher in selectivity to formic acid as well. Now I actually have a catalyst, right? In this case, the oxide helps the metal in producing CO, but the metal also helps the oxide in producing formic acid. And I get a catalyst that's kind of bifunctional, right? I can select which product to get by choosing the applied electrode potential. And in this entire range, hydrogen evolution gets suppressed, right? So I call this win-win metal oxide interactions, right? Then, we try to understand what's actually going on, right? So the first thing is they do actually have electronic interactions, right? So the electronic interaction is, if we look at the XPS, then we find that there is some electron relocation from the silver to the tin oxide, right? So there's electron relocation, and that electron relocation actually helps the catalyst to suppress hydrogen evolution in that range. So if you look at the hydrogen evolution on silver, right? I mean, silver actually has a barrier like that. That's pure silver, right? But now in this case, we have electron relocation from silver to tin oxide. That makes the silver surface to be even more positively charged. And that is more difficult to bind the proton to form a hydride type of intermediate, right? So that the barrier is even higher, so that makes the hydrogen evolution to be even more difficult, right? So that the electron relocation actually explains why the H2 is suppressed. Then we look at those CO2 reduction pathways, right? So one is you go from CO2 to carbon monoxide, and that the key intermediate is this COH intermediate, and that is the potential limiting step. Then if we look at the silver itself, right, it bonds the COOH, but only with the silver-carbon interaction, and that one is not so great, so that the binding energy is, the binding is pretty weak. You get a pretty large step, right, energy barrier. Then if we have the tin there, the tin can actually bind another oxygen of this COOH intermediate, and then lowers the binding, that lowers the barrier and make that COOH pathway to be easier. Then if we look at the CO2 to formic acid conversion, that's different, right? On the tin oxide, that you have 2 tin atoms that are binding the OCOH intermediate. And that binding is so strong, so the desorption of that formic acid becomes the potential limiting step. Then if you have the silver and the tin oxide, again, the silver can bind to one oxygen, the tin can bind to another oxygen. Then this changes the reaction pathway. This changes the energies of the step, so that now the potential limiting step becomes this one, and it's smaller compared to the one that is on pure tin oxide surface. So in this case, is actually the silver and the metal oxide sites, they actually work together to bind the intermediates, and it changes the reaction steps so that the CO2 conversion to both products are enhanced. Okay. So this is an example of how a metal and actually oxide interact together, right? And then one more example on nanoparticle interactions is this one that we have recently found based on metal-metal interactions. Okay, so in this system, we actually have lead and palladium, two metals atoms on one electrode, and depending on the potential, we get different compositions, right? So if we operate in this negative potential, right, and then based on the Purbase diagram, both metals are in metallic system, right? So they are metallic, and the surface has quite a lot of lead and a lot of palladium, and that composition, that catalyst, can selectively reduce carbon dioxide to formate or formic acid. Then if we go to a different potential where the lead remains as a metal, but where the palladium remains as a metal and the lead gets oxidized, you get a palladium-rich surface. And that surface can selectively oxidize, formate back to carbon dioxide. Okay, now you look at this, right? This one is a lead-rich one, and it does CO2 reduction pretty selectively. And this one is a palladium-rich one, and it does oxidation of formate back to CO2, and it's more stable compared to pure palladium because there's some lead over there. Then, you think like this might be not so interesting. It converts A to B and then converts B to A, but it actually offers us a way of doing some energy storage. Say now if I have free electricity and I can run it in this in this negative potential range where I convert carbon dioxide to formate. Then this formate can be stored as a liquid fuel. Then in some other scenarios where I actually need energy, then I can run it in this more positive potential range, and I convert the electrode to be active for reoxidizing formate back to CO2, and then electricity will be produced. So with that single catalyst, I tune the potential, I tune the composition, I tune its catalytic properties, and that can make it switch between a catalytic electrode for electrolyzer and a catalytic electrode for fuel cell. So I can run it in two different modes, and that can be used to do energy storage, right? So if I run this in the electrolyte mode, I convert the CO2 to formate. I can increase the formate concentration almost to 1 molar in the solution. Then if I can run it in a fuel cell mode, I can consume it, right? And this can be quite stable for more than 10 days. Okay, so this is a metal-metal interaction. Then one final example regarding the carbon dioxide reduction is, where do we get the CO2 source, right? So in a lot of studies, or in most of the studies so far, the carbon dioxide comes from pure gas. But we all know that the carbon dioxide as a pure gas costs money, right? It's a commodity. You have to spend money. And what we actually want to convert is, for example, something that is coming out of the flue pipe, right? And these ones, they contain a lot of impurities, and more importantly, they actually contain quite a lot of oxygen in it. Then if you think about what else you want to convert those carbon dioxide that has been captured, for example, by a capture system. And those gases also contain a significant amount of oxygen. Then eventually you want to deal with the carbon dioxide in the air, which only has 400 or 500 ppm of carbon dioxide, but the oxygen is 20%, right? And then if we want to deal with those more practical CO2 resources, the oxygen is the problem. Then if we think about reduction of CO2 versus reduction in O2, O2 is certainly the easier one, right? And the redox potential thermodynamics is 1 volt easier compared to CO2. Then what would happen if we actually reduce CO2 in the presence of O2? Then it depends on what reactor you use. If you use a reactor where the oxygen, okay, it'll be very quick. It's dissolved in the liquid. Then, because the oxygen solubility is so low, it certainly can be diffusion controlled, so it's not so big a problem, but you are not looking at the real kinetics, right? Though if you run it in a more, electrolyzer compatible, like gas diffusion electrode flow cell type of thing, then you would see that, the real kinetics thermodynamics kinetics will come into play. So what we did is, if we use a catalyst, only 5% of O2 mixed with carbon dioxide can completely kill the activity of carbon dioxide reduction. So only 5% of O2, you see no CO2 reduction, all oxygen reduction. Right? Then what you can do is, because the thermodynamics is 1 volt the difference, so it's very tough to do by modifying the catalytic side. So what you actually need to do is you need to modify the environment where the catalyst is taking place. So what we did is we take a polymer from our collaborator in the UK and then put that onto a catalyst surface. And then now you have a a polymer that is porous, that can separate the carbon dioxide from oxygen to a certain degree. So now it ensures your catalyst is operating in a O2 deficient environment. So you can convert it to even when the oxygen is 20%, you can work. When it's 5%, you can work, right? And then this is physical, right? Then if we want to further enhance it, we can actually add something in it that can chemically interact with carbon dioxide. And that can further increase the separation and get it to even higher selectivity. So now with 90% oxygen, you can still convert the carbon dioxide. So with that, I would pretty much conclude the talk. And these are the conclusions. I'm not going to go over them again because of a time issue. And then the students who did the work and collaborators and also the funding agency. Thanks a lot.
Okay, we're a little over on time. Maybe just one question. If not, I'll ask one question. Great talk. On the first part of your copper sequence, I noticed you showed that there was an optimum potential where you saw methane on the copper, and then there's this change in particle size. I mean, do you think the selectivity is really driven by the particle size of the copper nanoparticles that are kind of formed from your porphyrin, or what's driving that kind of the optimums in the selectivity in terms?
Yeah, I think that's a good question. But of course, I think one thing is you gotta get the metallic nanoparticles for you to observe the methane first, right? Yeah. Then there is, but I guess the parameters are not controlled here in this case, right? So if we look at the potential dependence, one thing is the copper itself, right? No matter what the copper you have, should have some potential dependence in its selectivity. That's number one. Then number two is, in our case, the size of the copper is actually dependent on the potential. So you actually have a potential dependent size as well. So there are two factors that are coming into play. So I cannot really say that whether it is actually the size or it's actually the potential. But at that potential, at the same potential, if we compare to other copper catalysts, it is the size that gives you higher selectivity. Right? So that is the conclusion I could make.
Thank you so much. Wonderful.
Okay.